This is a brief introduction showing how phase retrieval can be performed with gradient descent, and we will later extend this to phase design. To do this, we will make use of some of the automatic differentiation softwares that are available now. And basically, we'll use these to automatically calculate the gradients we need for our gradient descent. For phase retrieval, you can imagine that what we start with is some point spread function, PSF, at the detector. And we're going to work back through our optical system to determine what the original phase was that produced that PSF. Gradient descent will work for this problem as long as you can simulate your optical system with a set of differentiable equations, and lucky for us, most of the time you can. Let's run through a quick example. So here is a target PSF that I have, and I want to work out what the original phase is. I'm basically going to start with some noise and use that to estimate a PSF. Now I will compare the reconstructed PSF with the true PSF, and my objective is to minimize the difference. Using gradient descent, I can then propagate this information back to the pupil so I know how to change the phase values to reduce my error. You can also perform phase retrieval even if the PSF you're working with is saturated. Essentially, before you calculate your error, you also saturate your reconstructed PSF. You can also impose other arbitrary constraints. Here is an example where we performed phase retrieval on this weird looking pattern called the quantum monodromy pattern. So right now, this is just a straight phase retrieval. If we wanted to add a constraint, all we need to do is add a term to the objective function. So in this case, for whatever reason, we've decided to impose a 4-phase coloring on the pupil. And so all we need to do is add in a term that penalizes phase values deviating from our 4 allowed phases. Now we're going to borrow all of the machinery we just used for phase retrieval and apply it to phase design. Essentially, the key thing that you need to do is switch out the objective function. So here you can see that instead of reducing error with some arbitrary PSF, we can perform phase design where we do a naive optimization of an APP chronograph by having a metric that says, get rid of all the starlight in the dark annulus while keep as much of the starlight in the central peak as possible. Another really cool application is in diffractive pupil design. So for example, the upcoming Ptolemy Space mission. So this is an ambitious mission aiming to detect exoplanets using high precision astrometry between Alpha Cent A and B. And it does this by measuring overlap between PSF fringes. The final design requirements for the Ptolemy pupil are subject to ongoing review, but essentially you want a flat top disk with a lot of peaks. The pupil must be binary with equal areas of 0 and pi phase to induce a null at the origin of the PSF, and regions in the pupil must be reasonably sized for fabrication purposes. We did have to come up with a tricky objective function to incorporate all of these constraints, but we basically just used it, ran gradient descent with a number of different initializations, and here are some of those really cool results. Hopefully you can see that this method of applying gradient descent to phase retrieval and phase design is really versatile and easy to implement, and you can simply plug and play gradient descent for any of these kinds of problems.